Units and significant figures. In this lecture, we will look at units, we'll look at systems of measurement, we'll look at uncertainty associated with measurement, significant figures, and then rules for significant figures in mathematical operations. The goals of this lecture will be to recognize and differentiate between units in the metric and English systems of measurement, and to understand and apply significant figure rules to measurements and calculations. So starting with units, units are important because units give meaning to numbers. If you just say 12, you have no idea what that reference is. If you say 12 inches, then you have an idea of what that number represents. So most numerical values will contain a unit as well. And there are two main systems of units. We have the English system and we have the metric system. We tend to use the English system more here in the United States, but the metric system is more widely accepted. So the English system, again, that's the version that we use in the United States. When we're talking about units of length, we're talking about inches, feet, etc. When we're talking about weight, we tend to use pounds and ounces. And with volume, we tend to use cups and gallons, etc. The metric system is the more widely accepted system. This is the system that's the standard for use by scientists and really the rest of the world. When we talk about length in the metric system, the meter is the base unit that's going to be used there. When we talk about weight, we're using the gram. And when we talk about volume, we're using the liter. So these are the typical units associated with measurements within the metric. Now within the metric system, there are common prefixes that are used, and we use these prefixes to give relative size to values. So you don't have to write out a billion, you can write out 10 to the ninth. Okay? And we can represent different units in different prefixes, and these are all within the metric system, and their mathematical meanings here. So we'll use these a little bit more in some calculations. So metric units, just to show if we're looking at length, just pictorially speaking, we said a meter was typically the length that we used, and a meter is equivalent to 1.09 yards, and a yard is 3 feet. So we have this relationship between English and metric system here. And if we're thinking about things that represent this size, a baseball bat is approximately a meter in length. In terms of mass, we said that a gram is a unit that we use in the metric system, but in the English system we use pounds. Well, a gram is much smaller than a pound, and you can see that a gram is actually 1/454th of a pound. And so thinking about weights and masses, 2 pennies, 5 paper clips, and a marble, these have masses of 5, 2, and 5 grams respectively. So nowhere near what the mass of a pound would be. In terms of volume, a liter is typically used as volume, and a liter is equivalent to 1.06 quarts. So just an example, so you have an idea of a liter, a bottle of soda represents a liter. When we are making measurements, we do have some uncertainty that's associated with measurements. Anytime a scientific measurement is made, there's always a degree of uncertainty, and that degree of uncertainty is based on the limitations of the measuring device that you're using. The last digit in any value, in any measurement, will represent the degree of uncertainty. So if we're looking here, we have uncertainty in measurements as an example. We're looking at ruler A on the left and ruler B on the right. Well, in ruler A, we're looking at centimeters, but the lines on this ruler are 1 centimeter apart. When we're taking measurements, we always estimate 1 decimal point beyond what we can actually see. And so we can actually see whole numbers here, 1, 2, 3, that represents 3 different centimeters. So we can measure for certain to this place. We can measure the positions here. So when we're recording, you have your reading that's going to take place based on where the measurement lies. In this particular case, we can see that we measure 1, 2, 3 centimeters, but this line has not yet reached the 4th centimeter mark. So we're going to estimate that last position that occurs between the 3 and the 4. So this 0.7 is the position that has some uncertainty associated with it. So this roller A, we can read and estimate this measurement to be 3.7 centimeters. In roller B, you'll see that the increments that are present here, we have our 1 centimeter lines, but then we also have lines that represent 1/10 of a centimeter in here. So on this particular roller, when we're measuring something, we can measure the value to the centimeter position, that whole number position. We can also, because of these lines here, measure to that 10th position, and we can make one estimate beyond what we can actually see, which will be that 100th position. So if you're looking at this line here, we can say this is 3.123456 3.7, and then we guess the position in between these lines of this decimal place. So we say it's 3.74. Now you may look at that and say that's 3.73 or 3.75. The point is that that last digit has uncertainty associated with it, and you report one beyond which you can actually see. Now the exception to that, if you're using a digital readout of something, then you would just record all of the numbers that are present, and the last number would automatically include that degree of uncertainty. We do have significant figures that are associated with our values, and I think it's easiest to think about significant figures in terms of if we're thinking about the United States and we're thinking about whether or not we have decimal points present or absent. So we know that to the right of the United States, we have the Atlantic Ocean. So when we're in the Atlantic Ocean, we're going to think about decimal point being absent. So decimal point absent. Atlantic absent. And when we're in the Pacific Ocean, we're going to think about decimal point present. So we have Pacific present. In either case, we're going to start out in the ocean and we're going to move towards the continental United States. So if we have a decimal point absent, we're going to start out here and move across the number from right to left. If we're in the Pacific Ocean and we have the decimal point present, we're going to start out in the ocean, move towards the continental United States, and work from left to right. When we do this, we're moving in either direction, and we're not going to start counting a digit until we get to a non-zero. Okay, so we want a non-zero digit. When we reach a non-zero, that's going to be significant, and all others after that will as well. So here we can look at some numbers. This first value here, we have a decimal point present. If the decimal point is present, then remember that means we're going to start out in the Pacific, and we're going to move from left to right across this number. So as we're moving from left to right, we're going to start counting when we reach the first non-zero. So here we have our first non-zero. We're going to count that as a significant figure, and then everything after that. So this particular number has 1, 2, 3, 4 significant figures in it. So we say 4 sig figs. The second number here has a decimal point absent. So remember, if it's absent, we're going to start in the Atlantic and move towards the continental U.S. We do not start counting until we get to a non-zero. And then everything after that will be significant. So in this case, we have 1, 2. This has 2 significant figs. So 2 sig figs. This third number has a decimal point present. So Pacific moving this way. We start with the first non-zero and we count everything after that. So in this particular case, the first digit we hit is the non-zero, so that's significant. We count everything after, so 1, 2, 3, 4, 5, 6, 7. This has 7 significant figures. The next number has a decimal point absent, so Atlantic Ocean moving this way. Start with the first non-zero you reach and count everything after that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This has 10 sig figs. And the last example has a decimal point present. Start in the Pacific, move towards the continental U.S. Don't start counting until you reach a non-zero. This situation, we have 1 significant figure present. So we need to be able to determine the number of significant figures in a value, and then we can apply that to different calculations. So significant figures in mathematical operations, if the mathematical operation is performed, then the final answer has significant figures that are dictated by rules for that operation. And we can look for rules for addition and subtraction, and we can identify rules for multiplication and division. With addition and subtraction, when you're adding or subtracting numbers, you're going to look at the total number of decimal places and report your answer to the least number of decimal places present. So for example, if I have 11.52 and 3.102, I can add these together and get a value. So the calculator spits out 14.622. Now in this number, my final answer can only be reported to the number of decimal places that are present in the value with the least number of decimal places. So my first number has 2 decimal places, and my second number has 3 decimal places. This means that I can only report my final answer to 2 decimal places. So I would have to round it at this position, and the answer would become 14.62. So with adding and subtracting, you are going to report your final answer to the number of decimal places that are present in the value that has the least number of decimal places. With multiplication and division, you're going to look at the total number of significant figures and report your answer to the number of significant figures that are present in the value with the least number. So in this case, we take 8.125 and we multiply that by 63. And when you do that, the number you get on the calculator, if we go through this process, it would spit out 511.875. So this is a number from the calculator, but we can only report our answer to the number of sig figs that are present in the value with the least. So here we have 4 significant figures. Here we have 2 significant figures. So I can only report this value to 2 significant figures. So when I do that, I can report it here and everything else has to be rounded. So this value becomes 510. This value has 2 significant figures in that answer. So you're limited by the measurement that has the least number of significant figures here. Now we can also express numbers in terms of scientific notation. Scientific notation, and when this transferred, my exponents came down. So this should say 1.731 times 10 raised to the 6th. And this should be 9.2 times 10 raised to the negative 4. That should be an exponent here. Okay. So in scientific notation, you have a value, so a number dot a number, and the number of decimal places will depend on the significant figures that you're reporting to. Then you have times 10, and it's raised to some exponent, and that exponent will depend on how many places you would need to move your decimal. So the values have a number followed by a decimal point and any other significant value, and then a 10 followed by an exponent. And that exponent tells you how many positions you would need to move your decimal to get back to the original number that you have. We often use scientific notation so that our numbers look cleaner, so we don't have these large numbers with lots of zeros and digits following them, or lots of zeros before them. So an example, here again is that structure. You have some coefficient, which is reported to the appropriate number of significant figures. You have an exponential term, which is that 10. You have the exponent, which is going to tell you how many decimal places you're going to move your number to. So we can report the following values in terms of scientific notation. So remember, we want number, decimal, and then whatever else is present, times 10. And then we're going to figure out, if we put our decimal place here, how many positions have we gone? 1, 2, 3, 4, 5. Okay. Now in this case, the number was a small number, so in order to get back, we would have to move it to the left 10 or 5 places. So we say 10 to the minus 5th. Okay. If in order to get back to the original number you move to the left, it's a negative exponent there. This second value, we would write 1.26. So the decimal was kind of assumed to be here, and we're moving it to here. So how many places would you have to go to get it back? We're moving right, so the value is going to be positive. So times 10, and here it's 1, 2, 3, 4, 5, 6, 7. 10 to the 7th. So we can express values in terms of scientific notation, which makes them look a little bit cleaner. So just an overview, we represent things in terms of significant figures, and these are the digits that have some certainty, plus we have one digit that's an estimated digit. We can have non-zeros and zeros, and they may be significant or insignificant depending on whether or not we have a decimal place absent or present. And so we would follow those rules to determine.